All right. So, continuing with urban canopy layer, if I look from top, take a top view, right, the urban area appears at mean roof level, because in an urban area you will have some buildings, etc., you know, this is. So, if I look from top somewhere, view it from above, I will see the whole thing at an average, you know, mean roof level, and of course, the other will be the interelemental spaces. So, you know, like from satellite or something, one can look into this, comprising of shadows and multiple radiation heat exchanges. Obviously, this will have lot of heat exchanges, right. So, for example, if I have a single building, for a single building, isolated building, this is the north direction and it is in northern hemisphere, you will find that this is the zone, this zone and this zone, you get sunshine hours 8 to 9 hours, right. So, if you are seeing from top, you will see the, you know, if there is a single isolated building and nothing else, just hypothetical, then you will see this area shaded, you know, you will see sunshine hours less than 8 to 9 hours. For example, this zone 5 to 6 hours, and this blackened portion, it would be shadow for most of the time, because sun is, this is winter condition. So, winter condition, let us say winter condition, right. Top of course, we will have all the time the sunshine hour complete, but in winter in northern hemisphere, altitude angle of the sun is usually low, this beta is usually low, beta of the sun is low, beta is low. So, sun rays come from the southern direction and it is, you know, it is in the south. So, it goes from east to south to again west, and therefore, shadow will be something like this. So, if you are trying to look from top, you will see this pattern depending upon the time of the day. This is just as an example for a single building, and we know the kind of radiation received, intensity of radiation received on various surfaces, this is known to us. Now, we are trying to see what causes, what you call, first we will define of course, what is urban heat island and what causes them. So, trying to build up the background for all this. So, one thing is there is a shadow pattern and a mean, you know, urban canopy would be the mean roof level. So, you will see roof level, shadows and sunshine, this is the kind of pattern that you will get it, and this will vary from time to time of the day, and radiation, quantity of radiation received is also depending upon the surface that is there, right. So, if I look at it, let us say this is radiation on 1 degree south latitude, right. So, this is in month of July in watt per meter square, month of July, because July will be actually winter in southern hemisphere. Now, if I will just make the northern right now here itself, I will change it to northern. This is of course September, this is in February, this is the summer, right. So, southern hemisphere, the sun banks on the northern side. Now, if I change this to north, this February will become, you know, it is September, okay, can be March, September will turn to March, July will be somewhere during January or February, and this will be more of July or June, this will be July. So, this will change in this manner. So, you get lot of radiation during the summer time, but in equator this is on horizontal surface receives in this manner, right. And if I come to on north surface 1 degree south latitude, this is their winter and this is the summer. Correspondingly, if I take north, right. So, this would be basically August and this would be, this is 1 degree and this should be south surface now. this would be June. Sorry, this will not be August or June, sorry, this will be, in fact, this will be January, this will be December and January, somewhere during winter months, basically December and January. So, it would change to this. So, this would be south first of all, and south will receive more radiation during the, this will receive this is December in fact, and this would be sometime in January or so. So, you will get more radiation on the southern surfaces in the winter, right, and that is how it is. Now, east and west surface, this will just get changed to west. For east and west in morning you get it always. So, this you get in the July, this is in the February for 1 degree south. If I make it 1 degree north, this months will change, this will become February, this will become July, and this surface still east and west still will remain same, west will remain same, but only months will change. So, you see close to the equator you get a radiation pattern which is not too far different in the surface which receives sunlight, it is not too far different in, it does not vary too much if you are close to equator. But if you go away from equator, let us say same one, this was of course south surface. So, this is north surface in northern hemisphere 1 degree north, this will become February, this is December, months will also change accordingly. So, if close to equator, north and south surface both receives radiation, and winter as well as summer some radiations, and east west both gets radiation. But if you come to radiation for 33 degrees south, compared to that on horizontal surface, this January will of course corresponds to now June for north, and this would be for December, right. So, what happens is winter you receive much less, you will have much less sunshine hour and much less intensity of radiation as well. In summer the sunshine hour is longer, and sunshine hour is longer and radiation intensity is high. Now, 33 degrees south in India, of course, Indian subcontinent or northern hemisphere will correspond to in India, it will be somewhere correspond to Srinagar or some such place. 32 degree is Srinagar. So, around that zone. So, Leh or similar sort of places. So, where you get a lot of radiation in summer. So, this is for horizontal surface. While this was almost uniform in 1 degree, in 1 degree it was almost uniform, not very different, in horizontal surface sunshine hours are more or less similar, right. And away from equator, at latitudes away from equator, you find radiation pattern changing. Summer you receive more radiation, winter you receive less, and on north surface in case of 33 degrees south is you see it receives maximum radiation during their winter and minimum during summer. And if I change this to north, this will change to south, and this month will this will change to summer month, this will go to winter months, this will go to winter, and this will be summer months. So, summer you receive, south surface receives radiation during winter maximum. So, this is the radiation pattern, and east west of course will be similar, but hours should definitely get reduced because sun rises later, sets earlier in winter. So, that is how the radiation pattern on east and west, and north surface, I mean south surface in 33 degrees south receives only small amount of radiation during summer period, because day is long. So, sun rises slightly beyond east, that is somewhat a little bit on the south in case of southern hemisphere, in northern hemisphere slightly in the north. So, actually sunrise it will not be 12 hours, but sunshine period is more than 12 hours. So, therefore, north receives a little bit of sunshine in the summer period, and I mean east gets it and west as well, I mean sorry, not north in north. In case of northern hemisphere, it will receive something in the morning and something in the afternoon in summer time. So, this is how radiation pattern is. So, we see that radiation intensity varies depending upon latitude, although I am not going to a calculations, but we can actually calculate the out, and depends upon what we call day of the year or month or whenever it is represented day in the month, but it varies and also varies its latitude, varies upon its latitude or orientation of the surface and so on. So, actually if I look at it, I will have surfaces like this, right. So, sun's beams radiation is falling like this. Now, this radiation will then reflect, supposing I have another building here. I looked at single building earlier. Now, if I look at multiple many surfaces, I have now it will get reflected here, and actually it will have large number of interreflections, because this reflection will be again depending upon angle of incident will go here, this will go there, and there will be infinite number of reflections. So, this energy in a way, and every time it reaches here, some of it will be absorbed by this material. First directly this will absorb, and after first reflection, at the second reflection this will be absorbing this, and the third reflection again this will be absorbing this, fourth reflection this will be absorbed. So, all the it almost get contained into the surface. Supposing it was a horizontal surface, it would have gone and reflected, and in an urban area you have got large number of buildings, therefore, interreflected radiations, interreflected energy, that literally some of it gets absorbed or trapped into the urban area itself, right. So, although its quantity etcetera, so varies. So, depending upon which orientation it is facing, what is the H by W ratio, it will depend upon that, and one can model this, but I am not interested in modeling the same thing here. I am just introducing this subject to you. So, multiple reflections occurs, and that traps the energy, right. So, so that is what it is. So, incoming short wave radiation, if you recollect, we had the roof, this is for northern hemisphere, west wall, east wall, floor, this is what the short wave radiation, incoming short wave radiation will be. Incoming long wave radiation, because whatever coming from the wall, whatever is coming from the wall from a taller building to a nearby building, right, on a horizontal surface or roof, it will come some of it, and it might come from east to west. So, typically on an average, this is the long wave radiation which will be received by surfaces as well. So, this is time of the day, this is actually time of the day starting from 0 to 24 hours, I mean not in between only it is there. So, this will show you 0 to 24 hours, right, and we can typically we can look into the amount of long wave energy that goes out. So, this is short wave received and long wave energy, but whatever will be given away is long wave, because earth cannot either reflect or radiate short wave radiation at its temperature of 288 Kelvin. So, it will give away. So, this is what is long wave radiation received, this is what the short wave radiation received, this is what it will give away. Typically, this can show roof receives maximum obviously at the roof level on an average basis, walls, that is west wall, east wall, and this is the floor, right. This is the floor, because floor will get some radiation maybe coming through windows or whatever it is. So, that is how the radiation received will be. So, that is why we previously as we said, we found that different surfaces at different latitude receives different kind of radiations. This is of course on an average basis annual typically, right, and there will be short wave radiation it will be receiving, and whatever it will give away is all long wave radiation depending upon its temperature, right. So, roof will give away some radiations and so on, and net effect therefore is something like this. Net effect is something like this. So, roof receives radiation, floor receives some radiation, west wall and east wall receives radiation. This is all in northern hemisphere. So, net Q that we are talking about So, this is K which I defined earlier, L coming in, L going out, etc., on an average basis without going into details, and one can actually estimate this out. You can calculate this out based on heat transfers. Only I have given you the basic fundamental equations, and that is all. If you know average albedo values and all that, specific building one can model it very easily. But when you want to do for a larger area, it becomes, things will become complicated, or at least computational time required will be very, very large. So, you have to actually handle it in such a manner that it is actually, you can do that, but one can arrive at this kind of values. So, from this kind of, if I have now urban pattern, if I look at it, form, this is a flat surface, this will, its albedo could be 0.4, soil, etc., we talked about. But if I have this kind of surfaces, this 1.5% is the total surface area now, right, and albedo will now reduce, albedo will reduce, because good lot of it will get absorbed, amount going out will be reduced, some 70% reduction delta change, and if you have more buildings, there will be more absorptions, further absorption. So, that is how urban area tends to absorb the heat. Now, this, if you can understand that what we talked about, because sun's radiation receiving here of course it shows shadow. So, sun's radiation received here will be reflected there, reflected back, mutual reflections and all that, long wave radiation. So, net effect will be something of this kind, right, net effect will be something. Aerosol concentration, if you look at it, this is diameter versus number of particle. Usually particle size, generally they vary from, if you look at from 001 to 100 in micron or whatever unit you take. So, it is actually 10 to the power, variation is 10 to the power minus 3 to 10 to the power plus 3, or so something like 10 to the power 5 or 6, it will vary 5 or 6. So, it is not worthwhile plotting in linear scale. It is more convenient to take them in log scale. So, this is in log scale semi-log graph, and you see dn d log diameter one can put. So, it is the peak. So, maximum number of particle will be here, because n as a function of log d. So, dn d log d where it is 0, this peak, that is the maximum number of maximum particle would be there. So, you can see urban area aerosol is very much here, nucleation mode of course is somewhere there, and its particle size is somewhere there, and marine condition is this, quartz particle is this, continental and so on. So, you have urban condition is somewhere there, right. So, aerosols concentration of these sizes are very high, and that is where absorptions would be, absorptions they would absorb as well. So, this would affect the absorption. Now, next issue is, besides this radiation that we get it, we also generate some heat, vehicular traffic. Our appliances. So, these are called anthropogenic, the one generated by human being. So, in addition to whatever radiation I am receiving, there is anthropogenic heat generation as well. So, both together causes increase in the temperature or delta T. So, this is also, this is a further addition of heat that is on. Now, this one can actually get some idea about them, because we know for each type of fuel, for example, petrol, petroleum or diesel or hydrogen, how much energy they generate, fuel value etc. are known to us, some idea one can get it, but I am not interested giving in detail, one can estimate it. But typically large cities 60 to 160 watt per square meter annually. It will vary from summer to winter, because depending upon the location, latitude or social condition also. So, it will vary from country to country. In case of tropical countries, possibly where there are a lot of air conditioning, if it is used, the country where relatively more developed or area city which is using a lot of air conditioning units, summer anthropogenic heat generation might be very high compared to winter, because air conditioner should generate that heat. And medium cities density, medium density population 20 to 60, low density 5 to 20 watt per square meter. So, it varies, the values of course is what density depends upon the population density and a society, kind of society as well, but we do generate some. So, this is typically per capita per kilometer square, population density in terms of person per kilometer square, and if you have high population density, anthropogenic heat flux. So, this is somewhat for the American case, they had the data available, right, may not match with the Indian scenario the values, because we do not use that many number of vehicles as they do, but you can see where the population density is high, this value is also high. Well, this pattern would be true in any place where it will also depend upon kind of income of the people, expenditure capability of the people. So, you can see that this is, some of them are European, Berlin for example is there, Sao Paulo, Latin American, Philadelphia, Cincinnati, Los Angeles. I am trying to see if there are some Asians, there will be one or two, maybe London, Melbourne, Australia, Hong Kong, yeah. So, Tokyo. So, these are wherever data is available. So, generally tend to worldwide, it tend to show an increase. This is North America, this one, Europe is the triangular ones, Asia is the Asia is triangle, Europe is the square ones, Tokyo, and this is tropical, Los Angeles, A is tropical, B is dry. So, these climatic zones also they have given. So, it will depend upon that. One can get that, one can get some estimate of this from budgeting actually. You know how much energy you are consuming whole year, electricity consumptions from. So, those kind of data one can generate, but the idea is right, where you have higher population density you are likely to get more anthropogenic heat together with what we have seen naturally coming. So, therefore, this results in what we call urban heat island, right. Okay, let me see if I have a definition. Urban temperature is higher than surrounding. We have seen that sometime earlier we talked about microclimatic effect. There are several other effects of course that can affect your wind movement and so on, which I did not discuss today. But this heat issue that we are looking at. So, usually delta T is the temperature, this is the rural atmosphere, this is the urban atmosphere. Now, UCL is the canopy layer, this is the boundary layer, entry of the layer, that if we consider a layer or a volume around the urban area, the bottom layer is up to the roof level, canopy layer is up to the mean roof level or possibly at the roof level. And if you consider a layer above where it enters into the common atmosphere, that should be boundary layer up to the entry point, right, where you can ensure, you can consider the atmospheric boundary of that urban area. So, this is UVL and rural, and this there is a difference between the delta T. So, temperature difference between urban and rural will exist. Here you will have so urban heat island surface also, there are vegetation, here you have buildings, and subsurface also there will be a difference in temperature, urban minus rural, because there will be moisture you would have taken out and so on. So, rural subsurface. So, there is a difference between surface, subsurface and the atmospheric condition as well. And this, for example, a data for Tokyo and its surrounding is available. Temperature is higher. So, this is Tokyo, the yellow one. These are its surroundings, right. So, these are the surroundings areas. In fact, this is also somewhat urban. So, this is nearby, and surroundings have got similar pattern from 1907 to 2007 average temperature, right. Now, this measurement data should be available, and it shows that there is a temperature difference of the urban area, and that we realize also depending upon the situation. If you know the temperature in a urban area is much usually higher, 7-8 degrees higher at times. So, this is what is urban heat island concept. This is what is urban heat island concept. Now, this has been also proved by Salt Lake City from NASA. So, from satellite picture you can get ideas of temperature. The green ones shows the vegetation, the red ones are the warmest one, which are the built up areas. So, correlation with temperature of the greens are easily possible from satellite data. So, that gives you the idea. So, there is a there is urban heat island. So, how to reduce this if we want to reduce this, because it has got a cascading effect. Higher the delta T, you would possibly try to make it use more active system. Heating or cooling system. I mean cooling, of course, not heating, cooling, because higher temperature. So, more active cooling system you would like to, utilize, right, more active cooling system you would like to utilize. So, therefore, cascading effects means the more active cooling system means more anthropogenic heat will generate. So, more active, more anthropogenic, and therefore, it will have a tendency to increase it even more. So, therefore, we should look into some sort of reducing this from overall urban point of view. Individual building point of view, we have looked into energy consumption and so on, although we did not look into modeling, but we have looked into some ideas related to that. So, basically objective is to reduce energy use, reduce health risk, of course, right. So, urban and rural temperature you can measure, hotspot within the city you can measure, which has got highest temperature within the city itself. Then you measure air temperature, surface temperature, seasonal temperature pattern, day and night temperature pattern. So, one can measure this if one is looking at it. Basically, if you know that, then you can reduce the energy consumption and all, right. So, mitigation is required, I mean that would be a good idea, and mitigation strategy could be trees and vegetation. How does T do that? That we will see in the next discussion. Trees and vegetation. Well, green roofs also one can conceive, but there are problems with the green roofs. You have to have thorough waterproofing in your construction system of the roofing system, right, in a good quality construction. Cool roofs, you can have different types of passive concepts, but some of them are not so easily achievable. They need a lot of engineering or science or technology into it, but this can be easily looked into. So, at the urban planning stage or urban, not only planning stage, at the urban, if you are changing any urban pattern, taking decision related to urban. For example, decision related to change of floor area ratio in a city. The moment you change the floor area ratio, as you can see now from our discussion, you are making building taller. If you increase the floor area ratio, what is floor area ratio? Floor area ratio of total floor area divided by plot area. So, if I increase the floor area ratio, in fact, I am allowing taller building to come on the same plot, population density will increase, and not only that, population density will increase and it will also affect the all kind of temperature rise and things like that. So, urban heat island effect. Cool pavement, this can be done easily. Relatively cooler pavement in the sense that you do not have everything concrete surface, where there will be a lot of runoff, and smart growth. So, we will look into some of that quickly. One or two we will look into. Trees and vegetation. Trees and vegetation can also reduce stormwater runoff and protect against erosion, besides keeping it cool, because you have seen from that temperature is directly related to vegetation growth, the NASA photograph that I showed you. And cool pavement using paving materials on sidewalks, Now, pavements quite often people make sidewalk even concrete pavement, that is not the right thing to do, possibly if you do not want of course the urban heat island effect. And paving materials on sidewalk, parking lots, percolated concrete, there are several options available that remain cooler than conventional pavement. So, this is the mitigation strategy. I think with this we close.